Okay, here we are with the notes on section, oops, gotta move that around. Section 2.1, which is our first section about derivatives. We're gonna see what derivatives are, but first, this section is kind of uh, a conceptual overview of some concepts we've learned before to slowly sort of introduce this concept of the derivative so we can really understand it. And here are your first two warm-up problems. So in just a moment, you're going to pause it, and I'm going to pause the video too, and then I'm going to work out the problems here, and you can work them out on your own paper. And then after I pause it, um, you'll see the stuff I did, and then you can check your answers based on that. So here we go, pausing in one, two, three. Here we are back again with the answers. Um, so with the stories here, part A said I had just left home when I realized I'd forgotten my book, so I went back to pick them up. So going back means that you had to go home, and at home, your distance from home is 0. So that's what this represents here. That time where your distance from home was 0, that means you were at home. The time when you were going up here, that means moving away from home, because as time increases, your distance away from home is increasing, and then you're sitting here realizing it for a moment and not moving, and then your distance from home starts decreasing again back down to 0, and then you go back to school. So that's that one. This one, things are going fine. You're moving along. Distance from home is increasing. And then when you have a flat tire, you're not moving. So that means this should stay flat. It's flat because as time goes on, your distance from home is neither increasing nor decreasing. It's staying the same. And then it's fixed and you go the rest of the way to school. And for C, going out calmly means that the slope here was smaller, and then you speed up. That means this has a slope, a steeper slope. So you're going towards school faster over here, because for the same amount of time, when it's steeper, you're going up a greater increase in y. Uh, and then 1, the story I made up for it looks like it's steeper at the beginning for a bit here, and then flatter. It kind of steadies out to a flatter slope, meaning a slightly slower speed than it was at the beginning. It's a little bit concave down with that shape. So I just said I started off riding my bike to school fast, but soon got tired and went slower the rest of the way. And for warm up 2, one thing I meant to point out is that whenever you see interpret a number, interpret a result, it means you need to write a sentence about that in English that has to do with the situation that was described in real life. So, anyways, I found the work, I did the workout, got this, and the answer is negative 16 miles an hour. So that is the result, but then the interpretation, which is really what I'm looking for here, is that during this half hour, my average speed, oh, you can't see the word average there, average speed was 16 miles per hour riding towards home. Okay, I'm going to pause it again and then make some more notes. Here is the next topic we're going to talk about. This is sort of just about some different vocabulary terms that don't all mean quite the same thing. A lot of people think of velocity as just another word for speed. Like speed and velocity mean basically the same thing in everyday English, but in math and like physics classes, they mean or in engineering situations, they mean different things. And I want to go over the differences here. And distance and displacement are likewise different but similar. The main difference is that distance and speed, these ones here, are always just going to be a number. Which is always a positive number, in fact. Whereas the displacement and velocity represent the same basic concepts, except they can be positive or negative numbers, and they indicate direction too. So, for example, if I drive north for 30 miles, it's the same distance whatever direction I go. If I go north for 30 miles, or if I go south for 30 miles, or go east for 30 miles, those are all the same distance. And likewise, if I do it in an hour, that's my speed, is 30 miles per hour in whichever direction I go. Displacement and velocity, we're gonna indicate some kind of direction with them somehow. And you can do that with positive or negative numbers. Or if you want to talk about more advanced things, this is a little preview of like Calculus 3 and physics stuff that you do, you can have vectors which represent motion in all kinds of different directions. So you can have like a displacement vector, for example, could be like east for 30 miles or northeast for 30 miles or whatever angle you're talking about at whatever speed. And velocity, likewise, is a different velocity whichever direction you're going. So if I go 30 miles per hour north, that's a different velocity from 30 miles per hour south, even though it's the same speed. So let's just do a quick example of that. Here's another good place to pause it. Fill in these blanks here with numbers, include units, and if you're not sure, make a guess. Make a guess and pause it right here. 3, 2, 1, pause. All right, here are some answers. So if you're walking 5 meters towards a classroom door, the distance you walked is 5 meters, whichever direction you go, and you went at a speed of 2.5 meters per second, which is pretty fast. You guys can walk out the door pretty fast sometimes. Here is the displacement. Now, the displacement is negative because it's, when I say the distance from the door, how is that changing? It started off as 5 meters from the door, and then later on time, it was 0 meters from the door. So if you start at 5 and then go to 0, that's a negative change. So you can think of displacement with numbers kind of means the same thing as like a delta y, sort of. And the velocity is likewise negative, and you can see that in this graph here. If you start off at a distance of 5 meters from the door, and then in 2 seconds you're walking out the door, that you have a negative slope here. So just like with the example from the beginning here, when you have a negative slope here, here we had a negative slope with this one, that means your distance is your distance is distance from whatever that variable is decreasing over time. Here is the definition of average velocity, which we're going to talk about here. So if we're talking about the kinds of functions with the last few examples, were examples of position functions, like what we're talking about with S of t here, where the units of a position function are meters or centimeters or miles or inches, whatever. Some kind of distance is what a position function represents. Then given that function, either as a graph, by the way, or as a table, or with a formula for how to evaluate it, either way you have it, the average velocity means the same thing. This is the formula for it. Now, let's think about this formula for a second. Why does it make sense? Well, when you think of average velocity, the way we talked about it sort of briefly back in in the beginning of the class with the bonus section 0, average velocity usually represents a change in distance divided by a change in time. So if y is the output variable in your position function, the change in y represents a change in position. And you divide that by a change in time, and the way you get that is by taking one value of y minus another value of y, and likewise you take one value of t minus another value of t to get the denominator. I'll write this out in words here. By the way, a change in distance is also known as displacement, like we were talking about before. So a change in distance can be positive or negative depending on whether the distance was bigger before or bigger after. So for example, if at the end of your time interval you're closer to home or closer to the door, then when you subtract this, you'll get a negative number, and you'll end up with a negative velocity. So in other words, velocity is displacement divided by a change in time. Okay, so let's look at this question here. This graph gives you the average velocity of some kind of particle. It gives you the position of some kind of particle. So it starts off 2 centimeters from somewhere, and then it ends up at the end 4 centimeters from somewhere, because that's 4 over here. The input variable here is time. So give this a shot. I'll pause it and work it out. And 1, 2, 3, go. Here is my answer. So the change in distance here from S0 to 3 is 2. So it's a total increase of 2 centimeters. And that's a positive change because it was overall upwards here. You started from 2 and went up to 4. And you notice that you don't count the going up and back. You're only interested in where you ended up with displacement. So you don't say you went a total distance of 4 from 2 to 6 and then back down 2. That would be a total of 6 centimeters. And you would count that 6 centimeters if you're talking about the distance that you were traveling, by the way. So you could say 6 centimeters of distance divided by 2 seconds, and you get an average, 2 divided by 3 seconds would give you an average of 2 centimeters per second of speed. But we're not talking about speed here. We want to know average velocity. So why is speed different? Because you want a total of that much distance going forwards and then backwards of 6 centimeters, but your displacement is only really the difference in your position at the end minus where you started. So anyways, you end up with that 2 centimeters over 3 seconds gives you 2/3 of a centimeter per second. And this can be represented with the slope of this dotted line here. Because it was a horizontal change of 3 seconds and a vertical change of 2 centimeters. So the slope of that is 0.67 centimeters per second. I'm going to pause this to write another example for you to try. Okay, here's a weird little example. Just trying to think a little abstractly and visually at the same time here. So if we just have a graph like this that represents the position of an object, S of t as measured in miles, at time t hours, just copy a graph that looks pretty much like this and draw lengths for b minus a and for s of b minus s of a. And what I mean by that is just draw a line somewhere whose length is equal to this number, and then draw a second line whose length is equal to this number. If you are totally confused about what I mean by that, you don't even have to pause it right now. You can just watch me do it. If you do know what I mean, then pause it in 1, 2, 3, go. So this is all I'm talking about. That b represents the distance from the y-axis up to here. So if you take that distance, which is b, and then subtract away this distance that is a here, you get b minus a, which maybe I have room to write here. So that's b minus a here, and that's the same as if it's up here. And likewise, if you take s of b minus s of a, well, s of b minus s of a will be negative because s of a will be greater, but still the distance between these y coordinates here will tell you how big that distance is. Here's the next thing we're going to need to think about. Just one little brief thing here, and then we'll go into the main idea of the section. Another way of writing this notation for average velocity, your change in your displacement, change in position, divided by change in time, is instead of writing b minus a as just b minus a, you use another variable instead of b. You use h instead, which represents b minus a, how far apart they are. And then if you just add a to both sides of this, you move it over here, you get b is the same thing as a plus h. So then you can write this average velocity with this h notation like so. You replace the b with a plus h and replace the b minus a with h. And this makes sense maybe if we look at, think of a number line here. I'll just try to draw a little graph. So let's say that we have a is right here, and each of these little squares is 1 unit, so that b is over here. Then b minus a is the distance between these, and you can see that, yeah, let's write it right here. B minus a is how far apart these are, which is 6. But then if you just think of that number 6 as your value of h here, and just write it that way, then it kind of makes sense that if you do a plus 6, then b is the same thing as a plus 6. So that's why you can write it like this. And this is actually a more common notation than using b and a. Okay, I'm going to pause it here and then introduce the main idea, write down a bunch of stuff. You'll see it appear in a moment. Okay, here's the main idea of the section, is an example of how to measure instantaneous velocity. Instantaneous velocity is kind of a weird idea, so here's an example. You don't have to pause it to do this example. I'm just going to work through it. A grapefruit is thrown into the air with distance above the hand that it was thrown from, given by s of t equals negative 16t squared plus 48t after t seconds. How fast is it going at the instant t equals 1 second? So that doesn't mean between t equals 1 and t equals 2 seconds, or between t equals 1 and t equals 1.1 seconds, because those are all like intervals of time where you can find the average velocity the regular way that we've been doing. But instantaneous velocity is a different thing, because if you think about it, when I mean an instant, I don't mean any period of time. So the change in time from t equals 1 to t equals 1, if you think about it, if we were going to do delta y over delta t, the change in position over change in time, well, we would get s of 1 minus s of 1 divided by 1 minus 1. It's like your a is 1 and your b is 1. So from t equals 1 to t equals 1, the change is 0 in position. I meant to say feet here. I think I forgot to do that. So that many feet, so it's 0 feet divided by 0 seconds, and it's like, oh, it's 0 divided by 0, which we know by now is undefined. It doesn't make sense to say what was my speed if I went 0 feet in 0 seconds in this instant of time. So maybe to get an idea for what we mean by this, let's look at a graph of this function, which we have ready over here. So this is at 1 second right here. It looks like the height of the grapefruit is about 32 feet. And actually, yeah, if you plug in t equals 1 into this, you're going to get 32 feet there. So it's at 32 feet above the hand. This grapefruit was thrown very, very vigorously. And it lands after 3 seconds, you can see over here. But what do I mean by the velocity at 1 second? Well, I set up this thing here on, maybe I have to drag this over, where here the s of t is this red one you see, and this blue one, which you can't see right now, is a thing that I set up, which is going to be a line which we call the secant line. I need to move h for this to work. I'm going to pause it. Okay, I figured out the problem. I have to do it with my mouse. So what this line represents is what we call the secant line. So if I set h equal to 1 here, h represents the distance from this point right here, from t equals 1 to the next point on the line over here, which is at t equals 2. And so the slope of this line right now is actually 0, because that represents the average velocity of the grapefruit from t equals 1 to t equals 2. It went up to 32 seconds, it went up a little higher to 32 feet, I meant to say, above the hand, and then up 36 feet, and then back down to 32 again. So its displacement, its change in position over second 1 to second 2 is 0, and so the slope of this line is 0, and so the velocity is 0. But the question is, what happens if you make this this interval, the length from 1 equals 2, t equals 1 to t equals 2 a little bit smaller? So like over half a second is right there. Over half a second, this slope represents the, I'm going to zoom in a little bit. This slope here represents the average velocity of the grapefruit over that time. So it was going up at a rate equal to the slope. But then as h gets smaller and smaller, we can see that the slope of it, the change in y from one point here to another point, divided by the change in t, gets closer and closer to being like the slope of this line. Now it's not exact. I can zoom in some more here to look even closer at this thing. I don't know if you can tell, but they separate a little bit. They're going through this point and this point. If h is a little bit bigger here, then you can see their slopes are a little bit different. The slope of the blue one and the slope of the path of the grapefruit. But then I make h smaller again, closer to 0.1 and 0.15. 0.5 there. It looks like it's getting closer, but if you zoom in still, you can still see a difference. But anyways, what I want the instantaneous velocity to be is just equal to the slope of the line that just touches the grapefruit's path at one point. Touches the grapefruit's height function at one point, I should say. And doesn't touch it at 2 points. But if I'm doing this thing where we're talking about from t equals 1 to t equals 1 plus h over here, it's always touching it at these 2 points, which you can see if you zoom in close enough. But to get it, and if you then try to get it equal to just touching it at exactly 1 point, I'm going to slide this over to 0. And you can see what happens is the line disappears because this fraction I set up here, s of 1 plus h minus s of 1 over h, becomes 0 divided by 0. So again, the instantaneous velocity is sort of like undefined if you try to do it that way. But what we can do instead is look at what happens when you have very small moments of time, like 0.05 seconds before if h is negative, or 0.05 seconds after, and it looks like that gives you a pretty good approximation for the instantaneous velocity. And so yeah, let's look at a more formal definition. I'll pause it and write it out. Here is the definition of the concept we're going to use to measure instantaneous velocity. So when we say instantaneous velocity, we mean the same idea as with average velocity. We have this average velocity formula up here. It's the same thing, except I meant to write a here. It would have been the same thing, except I made that mistake. There we go. And so we're looking, if you ignore the limit, it's the same thing. But we're taking the limit of this thing, which represents the slope of the position graph between 2 points, or the average velocity, the limit of that slope as h, the distance between those 2 points, gets closer and closer to 0. And that's what we're trying to do with the graph on Desmos here, is make the distance between these 2 points get closer and closer to 0. And I can make it really close to 0 and get an idea of what that slope is. I can calculate that, but if it's equal to 0, it's undefined. So in order to calculate this limit, what we're going to do is plug in some numbers. I'll make a table that we can fill in just a moment. Okay, these are the tables I want to fill in. You can do this if you want to get some calculator practice. There's some tricks you can learn to make these things go faster if you practice enough. So you can fill these in, but let's look at what these represent first of all. So what I'm looking at is some heights for this first one of the grapefruit at some points very close to 1 second is this first one. So what height is the grapefruit at? And then the second one here represents the average slope of the, I shouldn't say average slope, the average velocity of the grapefruit over these intervals from 1 plus 0, I'm sorry, like if you 1 plus h to 1, or 1 to 1 plus h. So for example, if h is 0, then that represents s of 1 minus s of 1 divided by 0. So that one we know is going to be undefined. But what happens if we look at the slope at these places right near it? I'm going to figure these out with my calculator. Maybe you don't want to watch the whole thing, so I'll pause it in just a moment. This is the software I use, by the way. It's called, it's basically a graphing calculator like program that is just easy to use. So the first thing I want to do to find S of 0.999 would to be take this function negative 16 times 0.999 squared plus 48 times 0.999. Oh, it wanted me to say times here. And okay, so that comes out to be 31.984. And then next, I'll pause it here to do the rest of them. Okay, here's what I got for these other values for the height. Okay, also, I keep pausing it. Sorry if this ends up being edited really badly. But anyways, I made a mistake. I wrote down 39.984 here for some reason, but it was really 31.984. So now let's look at how to evaluate this fraction, this average velocity between t equals 1 plus h and t equals 1. The first thing is that if h is 0, s of 1 plus 0 minus s of 1 divided by 0, plugging in h equals 0 gives you 0 over 0, and it's undefined, so nothing goes there. Then what goes here will be s of 1 minus 0.001 minus s of 1 over negative 0.001. And to do that, we can use the fact that 1 minus 0.001 is 0.999. So we have these function values here. So let's calculate that here. This will be 31.984 minus 32 in the top, which is negative 0.016. So it's a decrease if you go backwards in time, which is kind of weird. And then, so if you do that answer, negative 0.016 divided by negative 0.001, see what we get is 16. And I think the reason why this is exactly equal to 16 is that we did some round off error before. When we got this to 0.984, it was really, if we're going to be a little bit more exact, let's do this a little bit more exactly, actually, because I don't want to say that it's exactly 16, because I know it's actually just really close to 16. So I'm going to take this number here, which has a lot more precision than just 0.984. And when we do that, minus 32, you get that answer. And that answer divided by negative 0.001 comes out to be 16.016, which is a little bit more precise. And notice the units of this are feet per second. So we had a negative change in the number of feet as we went backwards, divided by that negative change in time, which ends up giving you a positive velocity, which makes sense because we knew the grapefruit was going upwards at this point. And then we're going to get something similar for this other one here. Likewise, this comes out to 15.984 feet per second. And if we do it with this other value that we have, this one's going to be that 33.44. For this one, I'm not going to use all those digits of precision. Just 33.44 minus 32 is 1.44 feet about in those 0.1 seconds. So that divided by 0.1 second gives you 14.4 feet per second. All right, so what can we take away from this to actually answer the question that we have here, like how fast was it going at that 1 second, and we're using this limit to do that? Well, we can see for this very small fraction of time before, it was going a little bit faster than 16 feet per second, and then for a moment after it, for 0.001 seconds after it, it was going slightly slower than 15 feet per second, and then for over a 0.1 second interval, it was going 14.4 feet per second. So I think a pretty good guess, even though we're not really calculating it exactly yet at this point, is the instantaneous velocity also known as the limit as h approaches 0 of s of 1 plus h minus s of 1 divided by h, in this case, is approximately equal to 16 feet per second. And in fact, it turns out it is equal to that if we use some more advanced tricks, which we're going to learn about in a few minutes. Okay, this example, which is this using the same function that we had before, giving the height of the grapefruit above somebody's hand who's throwing it, let's get the same result, but instead of just making a table like this and looking at a graph, let's do it using algebra, meaning really proving it by manipulating the formula itself. This is a hard one if you haven't done it before, but if you want to try it, you can pause it, and I'll do it while it's paused. In 1, 2, 3. Here's the solution. So what we have here first is the s of 1 plus h. That means plugging 1 plus h in place of t here. So you have 1 plus h, quantity squared, 1 plus h, all times 48 here, the other one times 16. That's what that is. And then s of 1 just means plug in 1 into it and you get this. And then doing some algebra simplification, a bunch of things cancel out. Here you have a factor of h in the top and a factor of h in the bottom, so that as long as h is not equal to 0, this fraction is equal to 16 plus h. If h is 0, this fraction is 0, it represents 0 feet divided by 0 seconds, which is undefined, but the limit is always concerned with h being not equal to 0, so it's okay to do this with limits, and you get 16 feet per second. And so yeah, so that means that it is exactly 16 feet per second. It's not something close to 16, because when you do it numerically like this, there's all this rounding off involved. You don't know exactly how things are working. It might actually be like 16.00037 or something like that, and you don't know if it's exactly 16, but it gives you a really close estimate if you just use numbers close to h equals 0. But the algebra tricks here, like the stuff we did in section 1.9, hopefully you watched the 1.9 video before this one, will help you understand that you can really prove that it's exactly 16. And then we'll look at some more stuff next. All right, here is the next example for you to try, complete with, I made a copying and pasting mistake and included the cursor in the screenshot, so that's what that is. Anyways, I want to talk about how this instantaneous velocity, what does it have to do with the graph a little bit? And just really quick, let's look at the line I made that has slope equal to this average velocity. Back with the same thing with the grapefruit here. So yeah, like we said before, if we're talking about h is equal to 1, then that means you're at s of 1 to s of 2, and the average velocity there is 0. And as h gets closer and closer to 0, the slope of this line is getting closer and closer to 16, which you can't quite see here. But it is slightly different slope between slightly different values of h, but right at that point, if it's defined, it's close to 16. So that's what you want to think of as instantaneous velocity, is the slope of this tangent line, the line that only touches the graph at that very one exact point, which I can't actually do because with the way I set it up. So the slope of that is instantaneous velocity. So with that in mind, let's look at this problem here, and I'll pause it and work it out, and so can you. And 3, 2, 1. Okay, so I drew some slopes here, or some lines whose slopes have the numbers that we're talking about. So this little red one I made going from t equals 1 up to t equals 3, that's the slope between 2 points, so that means we're talking about average velocity. So the slope of this is a. B, the average velocity between 5 and 6, is the slope of the, I don't know if you can see it, there's a little line from that point right down to that point. So that's the slope between 2 points. You call that a secant line, or an average velocity is the slope of that secant line. So that's the slope of that is b. And then these blue ones I tried to draw just touching it at one of these points on the outside are C, D, E, and F. So this is, the slope of this one is C, the slope of this one is D, the slope of this one is E, and the slope of this one is F here. So the question is, if we're writing these from smallest to largest, remember, I think smallest generally means like least, so that big negative numbers are always the smallest things. So I can see F here has a negative slope. Excuse me. F has a negative slope, and it's a little bit steeper than the slope of B. So I think F is the least one here. And then the one with the next least slope, it looks like B. Whoops. B, and then the next least slope, meaning a negative number closer to 0 now, is E. Just looking at that, because you can tell that the slopes are getting steeper and steeper negative as you go down that way. On the other side, they are big positive numbers, and then they become not as steep, meaning smaller positive numbers. So the smallest positive slope is D, and then the steepest positive slope is C, and then that secant line A looks like it's right in between them there. And you notice these are exactly these slopes as you go from left to right. C to A to D to E to B to F, that they are decreasing in that order. So as you look at slopes of this thing, they are generally getting less steep. And then there's a point here where the slope is 0 somewhere. The instantaneous velocity is 0 at some point, and then it starts being bigger and bigger negative numbers, meaning continuing to decrease. So a graph like this, we're going to look at this more later on, but this is concave down. Concave down generally means the slope is decreasing. And so that's just a preview of how these things work with graphs. And let's look at some practice problems next. Here are the 2 practice problems to do at the end of this. I think these are pretty similar to what we did before. For practice problem P2 here, the P is short for practice. I would recommend using the same method we did back here. With like 2 tables like this is one way to do it. Or you can organize your work however you want, but you're gonna have to calculate a bunch of numbers. One thing I want to point out is that you should do this problem here using radians. That's important. That when you're calculating this, the input needs to be radians for this to work out right. All right, I'll pause it and do the work on my computer in 1, 2, 3. All right, here are these answers so you can check your work. Thanks for sitting through to the end of this video and working on everything. It looks like the video is going to be about 45 minutes long, which I'm guessing means it takes you, gosh, what, like an hour and a half or 2 hours to really do all the problems. Well, congratulations for making it this far, if you did them all. And I hope to see your video notes on Tuesday. So anyways, here's the answers that I got. With this one, the change in position is negative, so you end up getting negative angstroms per second. Angstroms, I always think, is a funny sounding word, a very angry sounding unit of measurement. And anyways, this one plugged in some values of h, so I end up with 2.2 or 2.02, and these are the things I got with my calculator. I don't know what this is approaching exactly. I mean, I got like negative 0.83 something, but I can't say what it comes out to exactly, so this is my best guess is negative 0.83. And we're going to learn tricks for doing this with some shortcuts in chapter 3. It turns out the actual limit is exactly equal to 2 times cosine of 2, so it should actually be more like negative 0.83229, but you don't know how to do that or what cosine of 2 has to do with this function, so that's just a preview of chapter 3, but it looks like we got something like negative 0.83. All right, see you in class.